Now we start optimization with an example in discrete time. So we assume time evolves discretely and is denoted by t. And we consider a household that lives for uppercase T time periods. And basically uppercase T would be the time point when the household ceases to exist. And we explicitly allow for uppercase T to be infinity, so for an infinite duration of household's life, which can be usually conceptualized with the notion that the head of the household maximizes basically utility of an infinitely lived dynasty. So it's not the household head herself who maximizes her lifetime utility, but basically she does this also on behalf of her children, grandchildren, great-grandchildren, and so on and so forth. And that usually justifies the use of an infinite time horizon. And from a mathematical point of view, interestingly, a problem stated in infinite time is usually easier to solve than a problem that is stated in finite time. Now, the utility function is the standard utility function that you all are very well aware of. So utility of households increases with consumption. And this is one particular time period, but the household lives for different time periods. So in the end, if we have the lifetime utility function, we will have to take the sum over all utilities at each point in time. We normalize the price of the consumption good to 1. That's just, we take it as the numeraire. We denote household's asset with lowercase a at time t, and we assume that the household has these assets at the beginning of the period t, and the household has an income wt at each period. And then we denote savings by S sub t, and if households save and have positive savings S sub t, then they earn the interest rate R on savings that they carry over from period t to period t plus 1. Now, as I said before, we set up lifetime utility as the sum over all instantaneous utilities at each point in time. We sum up from time 0 to uppercase t, so the end of the planning horizon, which could be infinity. And we discount each instantaneous utility by the corresponding discount factor, where beta is smaller than 1, and it's defined as 1 over 1 plus the discount rate. So the rate rho measures the discounting by which I put less and less weight on future instants, basically, because people are impatient, so they prefer utility today than as compared to utility in the future. So beta is smaller than 1, and it's raised to the power of t. That means the further in time you get, the higher t becomes, the more future utility is weighed down. So the further away in time you look at, the less weight you attach to the utility level at that particular time, and that represents discounting. And households maximize this lifetime utility subject to their budget constraint, and I've told you previously that you can write down the flow budget constraint in this optimization problem, but one can also write down the lifetime budget constraint, and the lifetime budget constraint actually follows from the flow budget constraint, where we have on the left hand side total consumption expenditures over the whole planning horizon. So that's consumption expenditures, and in period t0 they are not discounted, but for all periods higher than 0 there is a discount weight attached to the consumption expenditure. So this, the left hand side, is the net present value of lifetime consumption expenditures, and the right hand side is the net present value of income plus assets, basically. So you have initial assets plus total lifetime income, again discounted, so the net present value of lifetime income. And households maximize their lifetime utility by choosing a sequence of consumption for all the points in time, starting at time 0 up to the end of the planning horizon, and this sequence should maximize lifetime utility and fulfill the budget constraint. One possible way to solve such a dynamic optimization problem is by means of the method of Lagrange that you are already very well aware of from the standard courses in the master's program. And in this case, you would set up the Lagrangian function, which consists of the lifetime utility function, so the sum from time 0 to uppercase t, the end of the planning horizon, of the discounted instantaneous utilities at each point in time, minus the Lagrange multiplier times the lifetime budget constraint, where we bring all the terms on one side of the expression. And then we can calculate from this the necessary first order conditions for a utility maximum, and that are the derivatives of the Lagrange function with respect to the consumption values, but not only at one time point t, but for all time points t from 0 to the end of the planning horizon, uppercase t. And this gives us uppercase t plus 1 necessary first order conditions for the derivatives with respect to consumption. And then we have also the derivative of the Lagrangian with respect to the Lagrange multiplier, which replicates the budget constraint. So altogether, we would have uppercase t plus 2 first order conditions to solve for the uppercase t plus 2 variables, namely consumption from time 0 to time uppercase t. These are t plus 1 variables, and then the Lagrange multiplier, which is the last variable, such that we have t plus 2 variables overall. Now, in principle and in theory, that's solvable, but as you can already imagine, it becomes very cumbersome for a lot of time periods, basically. And often you encounter problems in overlapping generations models where there are just two time periods, basically, or two overlapping generations. In this case, one can easily use this method, but for more time periods, this is not really practical. Now, there is one possibility, which we will see in a second, to solve this problem nevertheless, and that is based on the notion that if people behave optimally between time t and t plus 1, and this holds for all time periods, then basically we can infer from two first order conditions here, namely for time t and t plus 1, for example, the optimal behavior for all time periods by using the method of Lagrange. So that's one way to simplify the approach, and that can be applied in many problems that you encounter, even though you have, say, a large number or a high number for the planning horizon, or even an infinite planning horizon. But it is often not possible to apply this method if we have a stochastic optimization problem, or if we have dynamic interactions, for example, in case of dynamic games, so strategic interactions. And in this case, we would need to use the method of Hamilton-Jacobi-Bellman, which we will also talk about later on. And this method of Hamilton-Jacobi-Bellman is also based on the notion that if individuals behave optimally between two adjacent time periods, and this holds for all time periods, then basically individuals also behave optimally over the whole planning horizon. Now, as I said, with respect to the previous slide, we can solve such an optimization problem if we just take two neighboring time periods, and now we do that for time period t and t plus 1. So we calculate the first order conditions with respect to consumption at time t and consumption at time t plus 1. Then we have, as we had on the previous slide, this first order condition here, and if we bring lambda divided by 1 plus r to the power of t to the right hand side, we have this expression. Now, if we calculate the same, or the derivative of the Lagrangian with respect to consumption at time t plus 1, we get a rather similar expression, just that all the time periods, t here, and t here, they refer to time period t plus 1 for this first order condition. That's basically just the same as here, but for the next time period. So therefore we have two first order conditions, and we can simplify them, put them together by dividing them basically. And if we divide them and bring the discount factor to the right hand side, then we see we would have beta to the power of t plus 1 on the right hand side, divided by beta to the power of t. So what remains is beta we have 1 plus rt plus 1 on the right hand side divided by 1 plus r to the power of t. So 1 plus r remains without an exponent. And here on the left hand side we would have the derivative of the utility function with respect to consumption in the numerator, and the derivative of the utility function with respect to consumption but in time period t plus 1 in the denominator. And that is basically a consumption-Euler equation that describes the optimal evolution of consumption over time, here in relation to how the marginal utilities change over time from that. And if we use a standard utility function, as it is used in the literature, an isoelastic utility function, which is a concave, or usually a concave utility function for recursive households, then we would plug in this particular expression for the utility function. So that's ct to the power of 1 minus theta. We have in the denominator 1 minus theta. That's just kind of a normalization. So if we take the derivative of u with respect to consumption, then the exponent comes down and it cancels out with the denominator, which is often quite useful. And we have the minus 1 in the denominator, and the reason for minus 1 to show up in the denominator is that only if the utility function is expressed in this form, we can solve it also for the logarithmic case, which is the case when theta goes to 1. Because if theta goes to 1, then we would have the situation that both the numerator and the denominator go to 0, and we can use the rule of L'Hopital to solve for the particular utility function in this case, in the limit when theta goes to 1. And using this method, one would find out that the logarithmic utility function results. So the logarithmic utility function is the special case of an isoelastic utility function when theta is equal to 1 or goes to 1 basically. Now if we use this utility function and plug it into this expression here and calculate the derivatives, what we would see is that 1 minus theta comes down, cancels with the denominator, minus 1 cancels out because it's a constant, so we would have ct to the power of minus theta in the numerator, we would have ct plus 1 to the power of minus theta in the denominator. Now the exponent has a minus sign, so if we switch the numerator and the denominator, the exponent becomes positive, so these two operations cancel out. So we would have ct plus 1 divided by ct here, to the power basically of theta, and we bring theta to the right hand side by taking the whole expression to the power of 1 over theta. So we would have the expression on the right hand side, 1 plus the interest rate, plus multiplied by the discount factor, and the whole expression to the power of 1 over theta. And that is the standard consumption Euler equation that you will encounter all the time in these discrete optimization problems in most economic applications. And you should familiarize thoroughly with this expression. We will also encounter a similar expression in continuous time optimization. Now, what does this expression tell us? What we see here is consumption in period t plus 1 in the numerator and consumption in period t in the denominator. And that is already optimal consumption. So basically what you have on the left hand side is the growth factor for optimal consumption. And the growth factor for optimal consumption is related to the interest rate, the discount factor, and the parameter of the utility function that is theta, and theta determines the elasticity of intertemporal substitution. So basically it refers to the willingness of households to substitute consumption over time in order to take advantage of interest payments. So it measures basically how willing the household is to save more today when the interest rate increases in order to get this additional income. So it's basically the willingness of households to depart from consumption smoothing. So if there is no interest payment, the household would prefer a smooth consumption path over time. So to consume the same amount of consumption at every time period, and that's follows from the concavity of the utility function typically. So households are risk averse, they would want to have the same level of consumption at each point in time. So they want to avoid a situation where in one period they end up with less consumption, because this reduction in consumption decreases their utility by more than an equal increase in consumption in another time period due to the concavity of the utility function. Now, if the interest rate increases, however, they can gain additional capital income by saving today, and consuming more in the future. But if they save today, that means that they decrease consumption today. So they have a decrease in consumption in one time period in order to buy an increase in consumption in other time periods. And the willingness of households to do that is the willingness of them to depart from consumption smoothing, basically, to take advantage of additional interest income. Okay, so what do we see here? What we see here is that the consumption growth factor, the optimal consumption growth factor, will be above 1, which means consumption increases over time, because then CT plus 1 would be larger than CT, if and only if the interest, 1 plus the interest rate, multiplied with the discount factor is above 1. So that means that the interest rate that the financial market pays to the individuals is so high that it overcompensates individuals' impatience. So individuals would want to consume today due to their impatience to some extent, but if the interest rate is so high that it overcompensates the households, they would choose more consumption tomorrow than today, and they would have an increasing consumption path over time. By contrast, if the interest rate is so low that the product of 1 plus the interest rate times the discount factor is smaller than 1, then we would have that consumption shrinks over time. So if consumption shrinks over time, we have that CT is larger than CT plus 1 and the consumption growth factor is smaller than 1. In this case, households would consume more today and possibly run down their assets and therefore can only consume less in the future. So the consumption path would be declining and the consumption growth factor would be smaller than 1. So basically, the slope of the consumption path over time depends on the product of the interest rate with the time discount factor, of the basically interest factor, because it's 1 plus the interest rate with the time discount factor. And the elasticity of intertemporal substitution mediates the process. So that's the exponent. And basically, the larger the exponent is, the more willing households are to take advantage of a higher interest rate to shift consumption over time. So the elasticity of intertemporal substitution, which is the exponent here, is higher if theta is smaller. And then they are more willing to shift consumption over time. Now, this interpretation is very important, and you will often encounter this consumption-Euler equation or consumption-Euler equation in similar forms in all different types of economic models. So basically, that's at the core of all growth models, that's at the core of almost all business cycle models, and that's a basic version of this consumption-Euler equation. In many business cycle models, for example, you will also have a term that relates to the evolution of inflation over time. Here we have a deterministic model, so that everything is known in the future, but in business cycle models you will have stochastic terms, so you will have expectation terms, and so on and so forth. But at the core, all of these expressions go back to this consumption-Euler equation and the interpretation that I've just given you. Now we can illustrate the consumption-Euler equation by means of a graph where we plot consumption in period t on the horizontal axis and consumption in period t plus 1 on the vertical axis. Then we have the intertemporal budget constraint, and this has a slope of minus 1 plus the interest rate. So that's basically the price with which we can shift consumption over time. If we sacrifice a certain amount of consumption today, we can buy 1 plus r times the amount we sacrificed in additional consumption tomorrow. That's what the intertemporal budget constraint and the slope of the intertemporal budget constraint tell us. Now what we could do is we could consume everything in period t and nothing in period t plus 1. So this point is in principle feasible. Optimizing agents would not choose such a point, as we will see later on, but in principle it's feasible. Then we would have consume all the income in period t, save nothing for period t plus 1 consumption, and we would be here. And basically every point along the intertemporal budget constraint is feasible. Now it depends, the point that is chosen basically by optimizing individuals depends on the preferences of households, and they determine the location and the slope of the indifference curves. And I've drawn two indifference curves here, one for a patient individual and one for an impatient individual. And the patients and basically the location of the indifference curve is determined by the parameter beta, by the discount factor. And the curvature of the indifference curve is determined by the elasticity of intertemporal substitution, which is 1 over theta. So for the patient individual, basically the best choice would be here, so that would lead to the highest indifference curve for this individual. And this individual would sacrifice a lot of period t consumption in order to be able to consume much more in period t plus 1. That's why it is patient. So beta is rather high. It shifts the indifference curve basically upwards. And for the impatient individual or comparatively impatient individual, we would have a lower beta, and the indifference curve would be shifted downwards. So this individual sacrifices less of consumption in the first period, in period t, and therefore can buy less additional consumption in period t plus 1. So in principle, we can solve dynamic optimization problems by means of the methods of Lagrange and Kuhn-Tucker, as we've just seen. However, as I also said, with more choice variables or in stochastic environments or with strategic interactions, this might become impossible or very cumbersome, basically. And therefore, we will consider a powerful alternative to the method of Lagrange and Kuhn-Tucker in discrete time optimization problems, which is called dynamic programming. And the idea is, again, based on the notion that you can break down the problem of optimal behavior over infinite different time periods to one between two time periods, namely the current period and the future, with the assumption that if you behave optimally between today and the future, and you extend this for all time periods, then by induction you will also behave optimally for all time periods t, and therefore if you behave optimally between two time periods, you will behave optimally over the whole planning horizon. And with this notion, one can set up the Hamilton-Jacobi-Bellman equation and solve the dynamic optimization problem in a way that fits much better to more complicated problems. To do so, we denote or define variables that can be chosen by the individual or the household at each point in time as the control variables. In our case, consumption would be the control variable. And these are typically flows, so consumption can be chosen by the individual arbitrarily. So the individual can choose to consume nothing or to consume a very high amount. And then a second type of variables are called state variables, and they are typically stocks, and they are linked over time by the decisions of the households on consumption, but they are predetermined. These are assets, for example, in most of economic interpretations, and you cannot choose assets at one particular point in time because you start your period with the assets that you had in the previous period plus the interest payments on your assets, and you can only influence the evolution of assets over time by the choice of the control variables. So if you choose higher consumption level today, then you will probably run down your assets, and if you choose a lower consumption level today, you will save and accumulate assets, for example. But the past stock of assets was determined in the past. It cannot be changed by period t choices anymore. So these state variables are predetermined and are typically stocks. Now, as I said, the choice of consumption of the control variable affects the stock, which we denote by xt here, in the next period, xt plus 1. And the initial level of the stock in the first period of the choice is typically exogenously given. Now the utility function is again given by the instantaneous utility function at each period in time. at each point in time, and we take the sum over all the periods for the choices starting at time 0 up to the end of the planning horizon. And the dynamic constraint then links the future state variable to today's level of the state variable and today's choice of the control variable Ct. So that determines the evolution of the state variable over time. It is therefore the dynamic constraint, which will be the flow budget constraint in our formulation. Now the first step for the dynamic programming problem is to write down the Hamilton-Jacobi-Bellman equation. And this can be done in the following way. So we know the dynamic optimization problem is to maximize lifetime utility by choosing a sequence of consumption from time 0 up to the end of the planning horizon, subject to the dynamic constraint, the flow budget constraint later on in economic interpretations. Now the most important thing to note here is that this can be split into two separate parts, this lifetime utility function. If we denote by U0 this lifetime utility function here, we can split this up into the instantaneous utility function in the first period, so period 0 here, U of consumption at time 0, plus beta, the discount factor, times the future consumption discounted by beta to the power of t minus 1. So that's a recursive formulation basically, where we separated out first period instantaneous utility and add the discount factor plus the multiplied with the future utility level starting at period 1. So basically it's separating between today and all of the future that is to come. So utility is decomposed into instantaneous utility and discounted future utility. More generally, this can be done for any S, period S, that is smaller than the planning horizon. So we would have U sub S is then the sum over all future instantaneous utilities discounted with beta to the power of t minus s. So this can be split into instantaneous utility in period S and all the future utilities from period S plus 1 onwards. So that would then be UC sub S plus beta times U sub S plus 1. And the same principle as before can be applied to the value function of the problem. The value function being the function that links maximized utility levels already. So after the maximization problem would have been solved, if we plug in the optimal consumption levels, we would get the value function with the maximized utility. So if we denote this by uppercase V, given the state variables over time, which is by definition of the value function the maximized utility U sub S given the optimal consumption stream from time S onwards to the end of the planning horizon, and this would be the maximized lifetime utility given the optimal sequence of choices. So now we suppose that the decision maker has already solved the problem that starts at time t plus 1 for a given state variable x t plus 1. So that would be the initial state variable, and we assume the decision maker has already solved this problem and behaves optimally for all future time periods. Now then the maximum attainable utility at time t can be broken down into instantaneous utility as of today and the maximum attainable utility afterwards given the choice, the optimal choice that leads to the initial value of xt plus 1 with which the decision maker starts in the next period. So in this case, we would then be able to break down this value function into the future optimal behavior. So that's discounted future optimal behavior with the value function that starts at time t plus 1. So that's already optimized. And we would have instantaneous utility today. And this is what we still need to maximize such that we get to the optimal path to xt plus 1. So by making the optimal choice today. And we have the flow budget constraint again, state constraint on x sub t plus 1. And now this equation here is called the Bellman equation, which basically states that we break down the problem into one of making the optimal choice between today and tomorrow. And we already know that an optimizing agent would extend such an optimal choice for the rest of the planning horizon. Now the idea that given the decision at time t, the subsequent decisions should be optimal starting at time t plus 1 is called the Bellman's principle of optimality. And one can solve the Bellman equation in principle for all time points t, and that delivers the optimal sequence for control variables. Now, if t is finite, then this can be done recursively. So you solve the problem for the last period, and then you always solve recursively forward until you are at the first period of the solution. So that's a recursive solution. However, this can be rather tedious for multiple time periods, and in case of an infinite planning horizon, it doesn't work for obvious reasons. Fortunately, as we will see, there are better methods to solve this problem and to gain more insights into that. And from now onwards, we focus on the infinite planning horizon. So how do we solve this dynamic programming problem? I will give a simple cookbook procedure presentation of the steps that are necessary to do that. So the first step is to formulate the Bellman equation and to insert the constraint, the dynamic constraint, into the Bellman equation. So we would have the following equation: v of xt at time t is u of ct plus beta of v of xt plus 1. Now for xt plus 1 we plug in the dynamic constraint, the right hand side of the constraint, which is the function f of xt and ct. And then we want to maximize this by the optimal choice of consumption. Now for this we can compute the first order condition, namely the derivative of the Bellman equation with respect to consumption at time t. Now this is the derivative of the utility function, of the instantaneous utility function in period t, plus now we recognize that inside the value function here for t plus 1 we have consumption t showing up here. So what we have to do is to take the derivative of the value function with respect to xt plus 1, which is what we have here, and then the inner derivative, the derivative of the function f with respect to ct, and set the result equal to 0. So that's the standard first order condition that basically states that at this point we would not be able to increase utility anymore by increasing or decreasing consumption at time t. So that's the first order condition. Now the problem of this first order condition is that a function shows up, namely the value function, that we do not know. So we have no idea of how the value function itself would look like. The good thing is that we can characterize the function by using the envelope theorem, and in the end, when we solve everything, we can substitute it out. So in the end, in the optimal choice, the value function itself would not show up anymore. And how we can do that is that we characterize the derivative of the value function depending on xt plus 1 using the envelope theorem. So we take the derivative of xt plus 1, which is the derivative of the expression that we have inside the curly brackets here with respect to xt plus 1, given that we have the optimal choice of consumption at time t plus 1, which is the case because of the definition of the value function. So we already have the optimal consumption choice. Now, since we have the optimal consumption choice already, we know from the envelope theorem that only the direct effect of a change in xt plus 1 matters. Although an individual would re-optimize and slightly change consumption at time t plus 1, this is of a second order importance such that we can ignore this term. So what we have then, if we take the derivative with respect to xt plus 1, is this term cancels out, does not depend on xt plus 1, and inside here we have the derivative of the value function with respect to xt plus 1, and then the derivative of the function f with respect to xt plus 1, but not anymore the derivative of the function f with respect to the optimal consumption choice, because although this might change, this change is of second order importance as compared to the change in the function f when xt plus 1 changes. So this simplifies the derivative of the value function v considerably, as we see here, so for this other term not showing up. And as we will see later on, we can then use this expression to substitute out the derivative of the value function in the first order. Now in step 3, we use the first order conditions with respect to the choice of ct plus 1 and ct to express the derivative of the value function with respect to xt plus 1 and the derivative of the value function with respect to xt plus 2. So these two equations are simply the first order condition with respect to consumption at time t, and then this equation iterated one period forwards such that we have the first order condition with respect to the choice of consumption at time t plus 1. So the first order condition with respect to consumption at time t is this here, and the first order condition with respect to consumption in time t plus 1 is this expression. And as you can easily see, this expression is just this expression here iterated one time period forwards. Now this has to hold, they have to be equal to 0 from the first order condition. And now we can isolate from the first expression here v prime, which is we bring u prime of ct to the right hand side, so we have minus u prime ct divided by the expression that we have here, the derivative of the function f with respect to ct, and the discount factor from here, which we also bring to the right hand side. So then we have isolated the derivative of the value function with respect to xt plus 1. In period t plus 1, or for the first order condition with respect to ct plus 1, we do the same. We also isolate the value function, the derivative of the value function with respect to xt plus 1 on the left hand side, but we also leave the discount factor here because this makes it easier then to substitute out this term here in the expression that we derived in step 2 on the previous slide. So therefore we have then on the right hand side minus u prime of ct plus 1 divided by the derivative of the function f in the next period with respect to consumption at time t plus 1. Again, of course, it's negative because we brought utility to the right hand side. And we leave the beta on the left hand side now. And then we use these two expressions here and substitute them into the expression that we've derived in step 2. Here we substitute in v prime of xt plus 1, so this expression here. And here we substitute in this expression here. And what we get is the next expression here. So that's basically on the left hand side we've substituted in this term. On the right hand side we've substituted in this term. Then we have this term here is still the term that we know from this expression here. So that's what we have here. And then, of course, the minus sign cancels out because it would show up on the right hand side and on the left hand side. And the beta that we would have in the denominator on the left hand side, we multiply it to the right hand side and then it shows up here. And we have this expression. And the interesting thing now is that in this expression we don't have the value function or the derivative of the value function. So everything in this expression is known. We have the known utility function, we have the known constraint, the function f. So basically we substituted out the value function and the derivative of the value function and have the solution to the optimization problem just in terms of known functions. And as we will see later, when we use standard utility functions and standard constraints, the result would again be the consumption Euler equation. So again, to summarize, basically the equation that we've seen on the previous slide is the Euler equation. It's just in a not so familiar form because we have a general utility function and a general function for the constraint, but basically it's the Euler equation. And if we plug in the standard functions, the isoelastic utility function, for example, and the standard linear constraint, then we would get the standard consumption-Euler equation, as we will see later on. As I said, this expression only contains the utility function and the function of the constraint, which are both known, and the value functions, which are typically not known, they have been eliminated. Now we do an example, again an intertemporal savings decision of households. So basically an intertemporal consumption allocation. The utility function is as before, so as we're already familiar with. We take the sum from time 0 up to the end of the planning horizon of the discounted instantaneous utilities. We denote assets by lowercase a t, the state variable, and labor income by wt as before. And then the dynamic budget constraint is given by the following here. We have that assets at time t plus 1 are assets from the previous period multiplied by 1 plus the interest rate. So basically these are last period's assets plus the interest earnings on last period's assets. So that's capital income basically, this part, and plus capital carried over from the previous period. And then we have an additional term, and that's current period savings, namely the wage income that I get minus the consumption expenditures. That can be positive, that's when I save and the consume less than income in period t, and it can also be negative, then I consume more than my current income, so I would have a negative term here. And the same holds true with overall assets. So overall assets can increase, that's when I save, and they can also decrease if consumption expenditures are very high, that's when I dissave. So basically assets at time t plus 1 depend on the state variable of the past and today's choices of the control variable ct, and exogenously given labor income. In this particular case, it's exogenously given. In typical macroeconomic models, labor income depends endogenously on the choices of firms to employ workers and on the choices of households to supply labor. Now the first step in solving this intertemporal savings decision is to set up the Bellman equation. That's the value function today with assets at time t, which is to maximize instantaneous utility by choosing consumption ct, given that we have future optimal choices with assets from time t plus 1 onwards. Now assets at time t plus 1 onwards are determined by the asset accumulation equation that we had on the previous slide, so the dynamic constraint. Now the first order conditions from that for the optimal choice of consumption is the derivative of the instantaneous utility function with respect to consumption plus the derivative of the value function with respect to assets at time t plus 1 multiplied with a partial derivative of assets at time t plus 1 with respect to consumption. And we see immediately from this expression that this derivative is minus 1. So this term here is minus 1, and if we bring the negative term then to the right hand side, we would get this expression here, so that the derivative of the utility function with respect to consumption has to be the discount factor multiplied by the derivative of the value function with respect to assets at time t plus 1. And the interpretation of that is that at the optimal choice, the marginal instantaneous utility gain that I have today by having higher consumption has to balance off with the decrease in the discounted future marginal utilities for the associated decrease in assets at time t plus 1 that I have to sacrifice when I consume more today. And at this point where the income gain from consuming, utility gain from consuming more today balances off with all the future utility losses, at that point I cannot change consumption anymore and attain a higher lifetime utility level. Now in the second step, we again characterize the derivative of the value function with respect to assets at time t plus 1 using the envelope theorem. So we have the derivative here, and we have the derivative of on the right hand side of the Bellman equation with respect to assets at time t plus 1. Now the first part here only contains consumption at time t plus 1, so it drops out when we take the derivative with respect to assets at time t plus 1. And here we have beta times the value function given assets at period t plus 2. So here we have beta times the derivative of the value function with respect to assets at time t plus 2, and assets at time t plus 2 depend on assets at time t plus 1. So we have to take the partial derivative of assets at time t plus 2 with respect to assets at time t plus 1. And here we know already from the asset accumulation equation that this derivative is equal to 1 plus r basically, and we use this fact here. So then we have this expression for the derivative of the value function with respect to assets at time t plus 1. Now we use this and the first order conditions to get rid of the value function and the derivative of the value function in these expressions. So again, we can use from the previous slide the first order condition. This one here we express v prime of at plus 1 in terms of u prime of ct and beta. So we bring beta here on the left hand side. So we would have v prime at plus 1 is equal to u prime of ct divided by beta. And analogously, we can do this for the first order condition with respect to consumption at time t plus 1, which is just the previous first order condition here iterated one period forwards in time. And here we want to substitute out for this whole term here, so beta times the derivative of the value function with respect to assets at time t plus 2. So we let the discount factor on the left hand side, and we can then substitute this expression into the derivative of the value function with respect to at plus 1. If we do that and substitute the information from the first order conditions into the derivative of the value function, then we see we substitute this term here in here and this term here in here, and what we get is this expression here. And this expression can be rearranged where we bring all terms involving the derivatives of the utility function to the left hand side and the rest to the right hand side, and then we would have the ratio of the marginal utilities in period t and t plus 1 with respect to consumption, and on the right hand side we would have the parameters, the impatience of households as represented by the discount factor, and 1 plus the interest rate as what the financial market offers to compensate individuals for impatience. And now this is already, we are familiar with this expression already, it's the Euler equation, and this can be seen particularly well when we again assume an isoelastic utility function, and if we take the derivatives and plug that in, what we get is the consumption Euler equation in discrete time as we had it before, where again we have on the left hand side the growth factor of consumption, on the right hand side we have 1 plus the interest rate times the discount factor. So again, if the term in square brackets is above 1, then also the consumption growth factor is above 1, meaning that individuals consume more in period t plus 1 than in period t, so the consumption path is upward sloping. And if it's smaller than 1, so then impatience of households would be greater than what the financial markets offer to compensate impatience, then the term in squared brackets would be smaller than 1. If it is smaller than 1, this implies that consumption in period t is larger than consumption in period t plus 1, and the consumption path would be downward sloping. Individuals would consume more today and less in the future. And again, the strength by which these differences between impatience and the interest rate affect household consumption decisions depends on the elasticity of intertemporal substitution, which is given by 1 over the parameter theta, that in contexts where risk plays a role measures the risk aversion of households and therefore the curvature of the utility function. So that provides again information on the optimal change of consumption over time. However, we do not yet know the level of consumption or the optimal level of consumption. And the reason is this is the general solution of the difference equation. It's not yet the particular solution. And for the particular solution, we would need again certain initial conditions or endpoint conditions, as we will see later on in this course. So if we have a certain initial level of consumption, then we can solve for the whole sequence, and we would also know the levels. And later on, when we deal with the Ramsey-Koopmans model, that's exactly what we will do.